Good morning, everyone. I'm excited to welcome you to today's presentation. The focus will be on becoming a professional plumbing and piping engineer. We'll cover key skills like design, installation, and testing. On this journey, we'll explore the main systems involved, including cold water, hot water, drainage, firefighting, and irrigation. We'll also discuss important standards and codes such as IPC, NFPA, AWWA, SBC, and ASHRAE. So, let's get started and discover what it takes to excel in this vital field. Let's talk about pipe materials and the key steps to ensure a proper installation. First, it's crucial to verify that you're using the approved material and the correct diameter for your application. This helps avoid any compatibility issues down the line. Next, always check that the pipes are clean and that the end cuts are square. This ensures a good fit and a strong, leak-proof joint. Then, make sure to use the correct joint method based on the pipe type, whether it's welding, threading, or some other connection method. Following the right technique is essential for durability and safety. Finally, remember to label and support the pipes according to the standards. Proper labeling helps with future maintenance, and support prevents sagging or movement that could compromise the system. Keeping these steps in mind connects directly to our overall goal of a reliable, high-quality piping installation. In this slide, we're focusing on the design and installation of water supply systems. First, let's talk about some fundamental formulas. The flow rate, which we denote as Q, is calculated by multiplying the cross-sectional area, A, by the velocity, V, so Q equals A times V. This helps us understand how much water is moving through the pipe at any given time. Next, there's the head loss, which essentially tells us how much energy is lost due to friction and other factors as water travels through the pipe. The formula here involves pipe length, diameter, and flow rate, specifically. Head loss is approximately 10.67 times L times Q raised to the 1.85 power divided by D raised to the 4.87 power. It's a bit complex, but it's crucial for designing efficient systems. Then we have the pressure equation. Pressure equals rho times G times H, where rho is the water density, G is gravity, and H is the height difference. This helps us determine the pressure at various points in the system. Moving on to installation steps, the first key point is to lay the pipe with the correct slope, at a minimum of 1 centimeter per meter, to ensure proper drainage and flow. Next, we need to install valves at branch points and at the end of the system to control water flow and facilitate maintenance. Finally, before putting the system into full operation, we perform a pressure test to check for leaks, then flush the system thoroughly and disinfect it to ensure water safety. These steps are critical for a reliable and safe water supply system. All these concepts tie back to our overall goal of designing efficient, safe, and sustainable water distribution systems. Let's take a closer look at the hot water system. The key to understanding this system is the formula for calculating the heat required, which is measured in kilowatts. Essentially, you multiply the flow rate in liters per second by the temperature difference in degrees Celsius, then by 4.2, and finally divide by 1,000. This gives us a straightforward way to estimate the energy needed to heat the water efficiently. Now, moving on to installation steps. First, it's important to locate the heater on the wall or ceiling where it can be easily accessed and maintained. Next, you'll connect the cold inlet and hot outlet using the appropriate fittings, such as IV and FC, to ensure proper flow. Installing a pressure relief valve is also crucial for safety, as it prevents excess pressure buildup. Finally, don't forget to insulate the hot lines to minimize heat loss, and always mark the direction of flow clearly. These steps are vital for both safety and efficiency, and they tie back to our overall theme of creating a reliable and energy-efficient hot water system. Let's talk about drainage and venting, which are essential for a properly functioning plumbing system. First, there's a handy formula to estimate flow rates. Flow equals approximately 0.0185 times the square root of the fixture units, giving us the flow in liters per second. This helps us size the pipes correctly. When installing, it's crucial to maintain a minimum slope of 1% to ensure proper drainage and prevent blockages. Next, remember to install cleanouts at every change of direction. These are vital for future maintenance and clearing any potential clogs. Providing an air vent at the highest point of the system is also key. This allows air to escape, preventing siphoning or vacuum issues. Finally, always test your system with a water head for at least 15 minutes to check for leaks. If there's no leakage during this test, it indicates your drainage and venting system is properly sealed and ready for use. All these steps help ensure your plumbing functions smoothly and reliably. Now let's take a closer look at the pump and head calculation. First, we have the formulas. The total head, represented as H, is the sum of static, friction, and minor losses. This is crucial because it tells us the total energy the pump needs to add to the fluid to overcome all resistances. When calculating the power required, we use the formula. Power in kilowatts equals the flow rate Q times the head H times 9.81, divided by the efficiency eta times 1,000. This helps us determine the energy input needed for the pump to operate effectively. Moving on to the installation steps, the first step is to align the pump horizontally on its foundation. Proper alignment is key to avoid unnecessary vibrations and wear. Next, we install a flexible connector and a non-return valve. These components help accommodate slight movements and prevent backflow, ensuring smooth operation. The third step involves priming the pump, which means filling it with water to remove air, and then checking the rotation to confirm the pump is turning in the correct direction. Finally, we run a test, recording pressure and current readings to verify everything is functioning within the desired parameters. These steps and calculations are essential to ensure the pump operates efficiently and reliably within the overall system. Now, let's take a closer look at the fire fighting system. First, the key formula we use is Q equals A times V, which helps us determine the flow rate based on the pipe cross-sectional area and velocity. Alternatively, the pump head we need is typically about 7 bar at the hydrant to ensure adequate pressure. When it comes to installation, we start by using red GI 40 pipes with grooved joints, which are reliable and easy to assemble. Next, we install isolation valves and drains at strategic points. This allows us to control the flow and perform maintenance when needed. After the piping is in place, a hydro test is essential, usually at 1.5 times the operating pressure for about 2 hours, to ensure there are no leaks or weaknesses. Once the system passes the test, we flush the network thoroughly to remove any debris, and then connect the sprinklers and hydrants to make sure everything is ready for an emergency. These steps are crucial in ensuring the fire fighting system is both effective and reliable, supporting the overall safety of the facility. Now, let's talk about thermal expansion and supports. The key idea here is that materials like steel expand when they heat up, and this needs to be properly managed in our piping systems. The formula delta equals alpha times L times delta helps us understand this expansion, where delta is the change in length. Alpha is the coefficient of thermal expansion, L is the original length, and delta is the temperature change. For steel, alpha is approximately 0.00017 per degree Celsius. When installing supports, we start by placing anchors at fixed points to hold the system in place. Then, we add expansion loops or bellows roughly every 30 meters to accommodate the movement caused by temperature changes. It's also important to check the spacing of hangers, about 3 meters for steel and around 1 meter for PVC, to ensure proper support. Finally, after installation, we need to verify the alignment of the piping system, especially following a thermal test, to make sure everything remains properly aligned and functional. These steps are crucial to ensure the safety and longevity of the piping system as it expands and contracts with temperature variations. Now let's talk about testing and commissioning, which is a crucial part of ensuring our systems are safe and reliable. First, we use specific formulas to guide us. The pressure test, for example, is typically set at 1.5 times the working pressure, giving us a safety margin to identify any potential issues. When it comes to vacuum, especially for chilled or special lines, we aim for less than 500 microns. This helps us confirm that the lines are properly sealed and free of leaks. Moving on to the steps we follow during testing. The first step is to fill the system and vent out any air, then pressurize it to 10 bar for about an hour. This helps us check the integrity under pressure. If there's no pressure drop during that time, we know the system is sound and passes the test. Next, we flush the lines until the water runs clear, ensuring there's no debris or contaminants. Finally, for potable water lines, we disinfect with a 50 ppm chlorine solution. This step is vital to ensure the water quality is safe for use. Overall, these procedures are designed to verify that the system is both structurally sound and hygienically safe before it goes into operation, which ties back to our overall goal of delivering reliable and safe infrastructure. Now, let's talk about the final stage, documentation and handover. This is a crucial part of ensuring everything is properly recorded and transferred to the client. First, we need to submit all the required documentation. This includes the Material Approval Request, or MAR, which confirms that all materials meet the specifications. We also need to submit shop drawings, both 2D and 3D Revit models, so the client can review the detailed designs. Next, the Method Statement and Inspection Test Plan, or ITP, outline how the work was carried out and how quality was maintained. Pressure test reports are essential to verify the integrity of the system under operational conditions. And finally, as-built drawings and the Operations and Maintenance Manual, or O&M Manual, provide the final record of the installed system and instructions for ongoing maintenance. Moving on to installation final checks, there are 3 key points to ensure everything is complete and ready for handover. First, we verify that the system has been fully tested, ensuring it operates correctly and safely. Second, we check that all labels and directions are clearly marked, so future users understand the system's operation. And third, the client must conduct an inspection and give their sign-off, confirming they are satisfied with the work done. This process not only guarantees quality, but also ensures a smooth transition from construction to operation. Proper documentation and thorough final checks are what make sure the system performs reliably and meets all expectations.